Hey everybody, in this video, we are going to take a Unit 9 test based on the topic of kinetics. Now, we will also have a free response question immediately after the multiple choice section, but let's get started. All of these questions for the multiple choice come from the Chemistry Olympiad, so they might be a little bit hard, but I think we can do it. Number 1. If elemental bromine is being formed according to the equation below at a rate of 0.056 molar per second, at what rate is bromide ion being consumed? So this reaction tells us that for every 3 moles of elemental bromine that is being produced, 5 moles of Br- is being consumed. So we can use this relationship in order to solve this question. Now, there are other ways, such as relating all the chemicals via a formula that I discussed in video 9.1, but I don't like doing that, so we're not going to do that. So let's write this out. 0.056 molar of elemental bromine per second. You can rewrite this by splitting the molar into moles per liter, so you get 0.056 moles of bromine per seconds times liters. Now you can do some stoichiometry here, because for every 3 moles of bromine that is produced, so 3 moles of bromine that's produced, 5 moles of bromide is consumed. So we can go right on ahead and do that. 5 moles of bromide is being consumed. Doing the math, 0.056 times 5 over 3 gives us 0.093 moles of bromide per seconds times liters, and reversing the math, we can get that the rate of consumption of bromide is going to be 0.0, not 0.00, but 0.093 molar of bromide per second. So the answer is D. Now let's try our hands on number 2. Thallium-201, a radioactive isotope used to image the heart, has a half-life of 3.05 days. How long would it take for a sample of thallium-201 to decay to 18% of its original activity? So I will get into activity in a future video in the far future, but for now, just think of the activity as the concentration, because the concentration or amount of radioactive isotope is directly proportional to activity. So let's just pretend that we are talking about concentration in this problem. So we know that radioactive decay is first order, so we have to use the natural log of the original amount. So let's just pretend that the original amount was, let's just say, A. And in the end, it says it decays to 18% of its original value. So originally you had A, and after some time, you only had 0.18 of A. So you multiplied the original by 0.18 to get the new concentration, which is a lot less. So our new concentration or activity is going to be 0.18 A. And this is set equal to K times T. Now, how do we find K? Well, we know the half-life, and we know that for first-order reactions, the half-life is always constant. And there's a special formula that we can use to calculate K from the half-life. The half-life, or the T1/2, is equal to 0.693 over K. And we know our half-life is 3.05 days, so 3.05D is equal to all this. But we need to solve for K. So to get K, you simply do 0.693 over 3.05 days to get K. And you get that K is equal to around 0.227 days to the -1. So now that we have K, we can plug it in here and solve the problem. So ln of this, so let's do some simplification. We know that the concentrations of A, or the activities of A, cancel out, So we're left with 1 divided by 0.18, and we get around 5.6. Now we have 5.6, and this is equal to 0.227 days to the negative 1 times the time. Now, I kept track of sig figs since at the beginning there's exactly 100% or exactly 1. So this is an exact number, but 0.18 is not an exact number. So that's why there are 2 sig figs here, and the natural log of 0.56 is about 1.71. Notice how 2 decimal places for 2 sig figs, and this is equal to 0.227t. Now, 1.71 divided by 0.227 gives us the time it takes for the stuff to go to 18% of its original value. And it turns out this time is 7.55 days. And is that an answer choice? Well, hopefully. That's C. Now let's take a look at number 3. We have this cool reaction here, and we have some values, and we have some instantaneous rates. So now we have to find the rate law. Well, our rate law is going to be equal to K times the concentration of, here, let me nickname things. I'm going to nickname this as A and this as B to make my wording easier. So this will be A to the X and B to the Y. So we need to solve for X and Y. Notice how in the first 2 rows, this is constant, but our B is changing. So this change is going to be 0.055 divided by 0.04, or it is multiplied by a factor of 1.375. Now, what factor is the first rate multiplied by to get the second rate? Well, let's divide 1.1 times 10 to the negative 5 by 8.1 times 10 to the negative 6. And be careful about this because you need parentheses. So I got that to get from here to here, you have to multiply by 1.358. Now, I feel like 1.358 and 1.375 are close enough, and because for a factor change of this, the rate is also multiplied by the same factor change. So because of that, I can assume that B will have an order of 1. So that's the first problem. Now what about our second problem? Well, the nice thing about this is that this is kept constant while this changes. So we know that we can multiply 0.028 by something to get 0.037. So 0.037 divided by 0.028, and we get that it is multiplied by a factor of around 1.32. Now what about the rate? 1.5 times 10 to the negative 5 divided by parentheses 1.1 times 10 to the negative 5. And I get that the rate change for this one is going to be around 1.36. Now I feel like these two are kind of different due to sig figs, and because of that, I believe that these are close enough to be considered about the same. So for a factor increase of 1.32, the rate increases by the same factor essentially. It's just 0.04 off, which I'll consider as error, and I get that X will be first order as well. Now we have to find the rate constant K. So how do we find the rate constant K? Well, we can use one row to do that. So we know that the rate for the first row is 8.1 times 10 to the negative 6 molar per hour, and this is equal to K times the concentration of A, which is 0.028 molar. So now I'm using parentheses and not brackets because we only use brackets if we don't know the concentration, but since we know it, we use parentheses. And we know that the second molarity is going to be 0.040 molar. And doing the math and keeping track of our units, I get 0.0072, and the units will be molar to the negative 1 and hour to the negative 1. So this is the rate constant, and it seems like B fits the answer that I was going for, because this is the rate constant, 7.2 times 10 to the negative 3, and we know that these two substances, A and B, are first order. So we're done with that. Let's do number 4. In which of the following ways may a catalyst increase the rate of a reaction? So a catalyst, remember, is a substance that causes the mechanism to change. So instead of having this, for example, you instead have an altered mechanism that is typically or probably always lower in activation energy than the original, and because of that, the rate increases when you add a catalyst. So the first part says it may alter the rate law. Now, does the catalyst alter the rate law? Well, remember, the rate law is equal to K times random substances, and they each have an order, of course. So if we change the mechanism, because remember, a catalyst changes the mechanism, then don't you think that changing the mechanism will cause different chemicals to appear in the elementary steps? So maybe instead of it being a one-step reaction where it goes from A to B, it might go from A to C first, and then it might go from C to B. So notice how the rate law might change, because if there was one elementary step, such as over here, then the rate law would be equal to K times A. But what if I said this was a slow reaction? So this mechanism is caused by an enzyme, for example. And let me try to spell that out correctly. So enzyme. And if this was a slow reaction, this means that the new rate law would be K times C. So I'll write C over here. And notice how the rate law went from Ka to Kc. So by altering the mechanism, or in other words, by adding an enzyme that altered the mechanism, you can potentially get a rate law that is different, because the elementary steps change, so the rate law might change as well. And all due to that, the catalyst may alter the rate law, so this is true. Now, does it decrease the overall activation energy? Well, of course, I just said that. So this is true too, and thus 4 is C. Now, number 5 is a cool problem because it involves the steady state concentration concept, and it says not to make any further assumptions about the relative magnitudes of the 3 rate constants. So we cannot assume that K1 is equal to K negative 1, because it's said that you can't assume the magnitudes. So we need to write a rate law based on this reaction. So the first thing I would like to do is to write an equality that shows the steady state concentration of this substance. And before we continue, let's rename all our substances, because I don't know how to say any of these, and if I wanted to, it would be super confusing. So I'll call this A, and where is the other one? Nope, that's the only A. I will call this B, so there are B's here and here, and I will call this C, I will call this D, and I will call this E. Now we know that B achieves a steady state concentration, so this means that the rate at which this is being consumed is equal to the rate at which it is being produced. So over here I wrote that, and we know that the reaction K negative 1 and K2 are consuming B, so the rate of K negative 1 plus the rate of K2 is the rate at which B is being consumed, since as you can see, for example, this reaction K negative 1 is causing B to be transformed into A. So what about the rate of production? Well, the only thing that produces B is K1, because A is being transformed into B. So the rate of K1 will be the rate of production. Now we can substitute all of these for their respective rate laws. So this one will be K negative 1, and I think our substrates are going to be these two, so B and C. And this is plus the rate of K2, so K2 times, well, let's see the reactants for K2, this and this, so B and D. And this is all equal to K1 times, what are the substrates for K1? That, which is A. So we have this nice little equality, and let me fix that to make it look nicer. It's a D. And now we can write a rate law to start with. So we never start our rate laws with the reaction that can go forwards and backwards, because we usually never start our reactions with equilibrium reactions if we don't have to. And even though this is not equilibrium, the forward and backward reaction are significant, so we just don't deal with that. Instead, let's deal with this reaction where it's only a forward reaction. So the rate law for that reaction is going to be equal to K2 times the concentration of B times the concentration of D. Now we can do some substitution because, as you can see, our B is an intermediate that gets produced and then consumed. So let's try to substitute B. How do we do that? Well, we can factor this part and move it down here. So we get that the concentration of B times K-1 times the concentration of C plus K2 times the concentration of D is equal to K1 times the concentration of A, and dividing both sides by this, we get the concentration of B is equal to K1 times the concentration of A over K-1 times C plus K2 times D. Now we can simply just shove this into here and do some substitution to get our rate. So rate is equal to, let's see if I can do this, K2 times K1 times A times D all over K minus 1 times C plus K2 times D. And we have to do some substitution, so we get this, which is written in green, and that matches answer choice D. Next question. Tert-butyl alcohol reacts with aqueous hydrochloric acid to give tert-butyl chloride. So the rate is equal to K times the concentration of CH33COH times H+. So with which mechanism is this rate law consistent? So we have to go down the list and see which one works. Now, especially for chemicals that are very large and complicated, I'd like to substitute them for letters. So I labeled each chemical with their own letter, and that made things easier. So for the first reaction, I substituted all the complicated chemicals with their letters, and I labeled fast and slow, and I based my rate law from the slow, and then I did some substitution by knowing that the forward reaction is equal to the backward reaction, so the rate law of the forward reaction is equal to the rate law of the backward reaction. And doing some algebra, we singled out the concentration of C, and we simply plugged it back in here, and we got that rate is equal to K times K1 over K-1, which can all be simplified to a generic K, so you could have written K here, and he multiplied that by A times H plus times Cl minus, and this does not match the rate law that they gave us, so this one is wrong. Now what about B? So we have 3 reactions, but the third reaction was a single arrow, and it was fast, and we don't care about that because we only care about the single arrow and the slow reaction, as well as the equilibrium reaction, which will help us substitute things. So the rate law was just K times C, but we knew that based on this equilibrium, that the rate law of the forward reaction is equal to the rate law of the backward reaction, and moving things around, we get that C is equal to all this, and we substituted that into our C over here, because this is equal to this, so we could plug it in here, and condensing all the K's into just a K, we get that rate is equal to K times A times H plus, which matches the rate law that they gave us. So it is consistent, so B is our answer. And I'm not going to go over C and D, you can do that on your own. Now, number 7, an irreversible reaction, A plus B to products, is studied under conditions where B is much greater than A. So they did something called swamping, and when B is 0.10 molar, a plot of 1 over A versus time is linear. When B is 0.3 molar the plot of 1 over a versus time is indistinguishable from the first plot within experimental error. What is the rate for this reaction? So what this problem is basically saying is that the order of a is going to be 2, since a plot of 1 over a versus time is linear as shown here. So we can write rate is equal to k times a squared times b to an unknown order. So we need to figure out what order b is. Now what they did in this problem is that they made b much greater than a, so we can assume that k times b to the x can be our pseudo constant. So this will include video 9.3 and 9.6. So our rate will be equal to k prime, because k prime is our pseudo constant that consists of k times the concentration of b to the x, since we know that the concentration of b essentially stays constant throughout the course of the reaction, as explained in video 9.6, and this is multiplied by a squared. So as you can see, we could actually graph this, and 1 over a versus time should be linear, and the slope will be k prime. Now, they're saying that when you multiply b by 3, the line does not change. So normally, the line will look like that, and the slope will be k prime, which involves k times b to the x. But when they multiplied the concentration of b by 3, it says that the line is indistinguishable, which means that it's the same. So essentially, the slope stayed the same. So we know that k prime is the slope, of course. So I don't know why I wrote k1. It's supposed to be k prime. And the slope essentially remained the same even though we multiplied the concentration of b by 3. So what's up? So this is saying that no matter what we do to b, whether we multiply by 3 or whatever, the rate doesn't change, or in other words, the rate constant doesn't change. So because of this, we can safely say that the order of b is 0, because by changing the concentration of b, it seems like our pseudo rate constant does not change. So this tells us that b will be 0 order, so x is 0, and thus our rate law will be k times a squared. Now let's do number 8. The rate of a reaction is 2.3 times faster at 60 degrees than it is at 50 degrees. By what factor will the rate increase going from 60 degrees Celsius to 70 degrees Celsius? So we have to use the Arrhenius equation, which states that the ln of the rate constant 2 over the rate constant 1 is equal to negative activation energy over R times 1 over T2 minus 1 over T1. So we can assume that K1 corresponds to 50 degrees Celsius, which is T1, and K2 corresponds to 60 degrees Celsius, or T2. So doing the math, we just simply plug and chug, and we know that our K1s cancel out, and we keep on plugging and chugging and keeping track of sig figs, and we get that the activation energy turns out to be 7.4 times 10 to the 4th joules per mole, and note that there is only one sig fig, but I kept 2 in order for us to be accurate in the next part. So I plug in the activation energy, and I want to find the ratio between K2 and K1 now. So doing some maths, I get that K2 over K1 is equal to 2.18. And before, we knew that K2 was 2.3 times more than K1. But now, as you can see, K2 is only 2.18 times as large as K1. So this means that our rate will increase not by a factor of 2.3, but by a factor of 2.18. So this means that it increased by less than a factor of 2.3, going from 60 degrees Celsius to 70 degrees Celsius. And note that when you multiply the rate constant by 2, the rate is also multiplied by 2. So initially, our rate was multiplied by 2.3 by increasing the temperature from 50 to 60 degrees Celsius. But now, our rate actually increased by a factor of only 2.18, since our rate constants only increased by a factor of 2.18. So that's how you go about thinking about that, and therefore, A is our answer for number 8. Now let's look at number 9. A sample of 0.900 moles of N2O is placed in a sealed container where it decomposes irreversibly to N2 and O2 in a first-order reaction. After 42 minutes, 0.640 moles of N2O remains. How long will it take for the reaction to be 90% complete? So this is a multi-step problem, and we need to think about this. So first order means we're going to use the natural log of our initial concentration, and in this case, we can pretend that the sealed container is going to be 1 liter, and by doing that, all these moles turn into molarity because 0.900 moles divided by 1 liter is 0.9 molarity. So we start off with 0.900 molarity, and we have to divide by the conditions after. So after 42 minutes, 0.640 molarity of N2O remain. And this is equal to K times the amount of time that passed, 42.0 minutes. So doing the math, the natural log of 0.9 divided by 0.64 will actually turn out to be 0.341. And this is equal to K times 42.0. And dividing both sides by 42.0, we get 0.341 divided by 42.0. And K turns out to be, well, actually, I want the minutes here. And K is 0.00812 minutes to the negative 1. Now we need to find out how long it will take for the reaction to be 90.0% complete. So what does that even mean? Well, if we start off with 0.900 moles, or let's use molarity of N2O, and we want it to be 90% complete, which means that 90% of the reactants have to disappear. So 90% of the reactants turns out to be, well, 0.9 times 0.9 is 0.810 molarity of N2O. So we need to use up this much stuff for it to be 90% complete. So we will be left over with 0.090 molar of N2O. So we can make these our new conditions. So our original condition was 0.900 molar over our final conditions after 90% of the reaction is done. So 0.090 molar. And this is equal to our K, which is 0.00812, and that's multiplied by the time. And doing the math, the natural log of 0.9 divided by 0.09, and we have to divide by 0.00812, and we get that the amount of time it takes for all this to happen is going to be 2.8 times 10 to the second minutes. And is there an answer for that? Well, 2.8 is around 280, and 284 is pretty close because we kind of rounded, so D is our answer. Number 10, changes in which factors affect both the rate and the rate constant for a first-order reaction. So we know that rate is equal to the rate constant times the concentration of A to the x power, and so on. So by increasing the temperature, we know for sure that it increases the rate. But does it increase the concentration? Well, I don't think so. Increasing the temperature doesn't really increase the concentration, so it must increase the rate. So 1 is correct. And if you remember from video 9.4, increasing the temperature increases the collision frequency Z, which causes the rate to increase since K is equal to P times Z times F. So what about concentration? Well, increasing concentration increases the concentration, and that increases the rate. But does that impact the rate constant? Not really, right? So this means that 2 is out, and thus number 10 is only A. Now for number 11, they give us the rate constant, they give us the initial concentration, and they give us the amount of time that passes. But notice how the rate constant is in seconds, and this is in minutes. So we got to change minutes to seconds, and doing the math, I get 0.036 molar, and that turns out to be B. So feel free to pause the video if you need to look at the steps, and that's all I wanted to do for this video. Have a nice day, everybody.